Welcome back, class, to Lecture 8 of Numerical Methods. Here we're going to switch gears a little bit, move away from optimization and root finding, and start thinking about bigger systems. Systems that have multiple equations that need to be solved simultaneously. This is going to introduce us to linear algebra and using matrices. So just as a review, hopefully by now you feel comfortable using derivatives and using the root finding methods with derivatives of equations to find optima, using the golden search method to find optima, and then parabolic interpolation to find those optimal points. So that's going to be the end of Unit 2, and now we're going to move into Unit 3, where we think more about systems of equations as opposed to a single equation. Today, I want to just start laying that foundation. So talking about matrix notation, identifying different types of matrices that we may come across. So the identity matrix, diagonal matrix, matrices, etc. And then talking a little bit about matrix multiplication. Up to this point, we've talked about element by element matrix operations, but now we're going to actually talk about matrix multiplication, where we're actually doing all those operations that we've been trying to avoid up to this point. Then we'll talk a little bit about converting systems of equations into matrix format, and then how we can solve these with MATLAB. Let's provide a little context before we jump in. So particularly in chemical engineering, we often have sets of chemical reactions, not just a single chemical reaction. So let's say we have a chemical reactant, and it can convert from, say, species A to species B. Species B can convert to species C, and species C can back convert to species A. This equation then could be written out the rate of the individual reactions, or the rate of change of the concentration of species A could be written as follows, where we have negative the reaction rate constant of A going to B, plus the rate constant of A going to C, plus the rate of B going to A, so K12, plus times the concentration of B, plus the rate of C going to A times the concentration of C. And we can do this for multiple different equations, right? So these three equations are what I need to tell me how my system is changing with time, right? I need each of these, and I need to look at them all at the same time. And particularly, if I'm interested in looking at what the concentrations of this system would be at equilibrium, I need to find the case where those differential equations, so that dya, dyb, dyc are all equal to 0. If you look at this, as I've shown here, we have 0 equals negative k12 plus k31 times ya plus k12 times yb plus k13 times yc, right? So it's just that equation equal to c. And what you'll see is this equation, or these sets of equations, are really linear problems and can be thought of as root finding methods. But instead of having only one equation, so say just the first one, the second and then the third equations all depend on each other. This means we're going to need slightly different techniques in solving these problems as compared to either root finding methods or optimization, because we have multiple equations that are going to influence each other. And this is true not only, say, for reaction kinetics, but we can think about this in heat transfer for those of you who are taking or who have taken heat transfer. We could think of an entire system of grid points where the temperature at any one given point is the average of its neighbors. So say here's a single point. I could take maybe its temperature there, and we could say that its temperature is equal to the average of the points to the right and to the left, as well as on top and on bottom. Right, so I could write this into a mathematical form. So Tm comma n is equal to the sum of the temperature on top plus the temperature on bottom plus the temperature to the right plus the temperature to the left all over 4. And we could write this out for multiple sets of temperatures. And what you'll see is each of these equations are going to be for a different point, and they all depend on each other, right? So we have all of these interdependencies. In order to solve these, we need to solve all of them simultaneously in order to get the answer for the temperature distribution or for the distribution of concentrations. And we're going to see this come up in chemical engineering a lot, where we have these interdependencies of one reaction on another. And we're going to solve them using matrix math. Before we get into the matrix math, I want to go through a few reminders on matrices and how we can deal with them. So first, I want to say that we can use matrices to represent these equations, because we're going to take, by taking all those different variables and coefficients and collapsing them into the matrix form. So just as a reminder, hopefully you guys are feeling quite comfortable with this by now. A matrix is going to be a rectangular array of elements represented by a single symbol, and usually that symbol has an uppercase, is represented as an uppercase letter. Individual elements or entries into this matrix are called elements, and they're represented by a lowercase letter, so maybe lowercase a, and they have these two indices that are going to tell us which row and which column it is. So first we write the row, so row 2, then column 3 would be a, lowercase a, 23. We can say a little bit more about the matrix by looking at its size, which is going to be given by the number of rows and the number of columns. So the number of rows may be m, the number of columns n, and we can refer to that as having a size m by n. So maybe a 3 by 4 matrix. Right. Now that we've gone over some of the generalities of matrices, let's go through some special types of matrices. In particular, matrices where m is equal to n are called square matrices. Right? This is because they sort of form that square. Within square matrices, there's a subset of different types of matrices. So the first one being symmetric. If you look at this top square of a symmetric matrix, you'll notice that while the diagonals are unique numbers, we have these equivalencies across that diagonal line. Right? So put mathematically, we have a symmetric matrix when a I comma j is equal to a j comma I, right? So these two numbers are equivalent. The 2 and this 2 are equivalent. 7 and 7 are equivalent, right? So we have a symmetric case across that diagonal. Now, the second type of special matrix is called a diagonal matrix. In this case, there's only numbers on that diagonal. So only non-zero cases are where a, I, comma, I can be not 0. All right, so this number could be 0, but all the other entries into this matrix are going to be 0. There's a special case of the diagonal matrix called the identity matrix. In this case, not only do we have zeros in all the spots that aren't on that diagonal, but that diagonal I is equal to 1. This is really important because the identity matrix is essentially our 1, right? We can multiply any matrix by it, and we get back that same matrix. Moving a little bit out of this symmetric and identical or symmetric type of matrices, we also have triangular type of matrices. In this case, it's sort of like the diagonal matrix, but we have only 1/2 of the matrix is filled with zeros. So the first type that I want to talk about is a triangular matrix, an upper triangular matrix. It takes its name because if you look at these rows and columns, they form a nice triangle, and everything else is a 0. So there's elements on the diagonal that are not 0, and there's elements above that diagonal which are not 0. It's called upper triangular because it's the upper rows that are filled and the lower rows which are empty. Similar, we have a lower triangular matrix. We once again have this triangle, and but this time it's those lower rows that have more elements while the upper rows are empty. And then we have banded matrices. These are cases where you have some zeros in the upper and lower column, but you see we have this band here. So there's all these rows or these diagonals that are filled, and they form these sort of bands, and either on the upper side and the lower side we have zeros. So these special types of matrices are going to help us take some shortcuts when we get into solving the matrix, solving for matrices. Let's talk about matrix operations. So the first thing that we may want to know is, are two matrices equal? We say that two matrices are equal if and only if every single element in the matrices are equal to every element in the second matrix. This means Aij, so element Aij in matrix A, must be equal to Bij, and it has to be for all I and j. Right? If I have one single element that doesn't match, the matrices are not equal. The next type of operation that we might want to know is about matrix addition and subtraction. So this is not the case of what we had before. So say AI11, A12, A21, A22. I'm not talking about taking that minus 5. I'm talking about taking two matrices and subtracting one from the other. So say B11, B12, B21, B22. When I subtract them, I get a matrix that's each element subtracted from the other. So A11 minus B11, A12 minus B12, A21 minus B21, A22 minus B22. And then the same thing would go for addition rather than subtraction. So as you'll see from this format, we require that the matrices have to have the same size. Otherwise, I'm not going to be able to take this element by element approach. The next thing would be scalar multiplication. So in this case, maybe say 5 times A11, A12, A21, A22 results in a matrix where we take that scalar and multiply it by each of the individual pieces. So 5A11, 5A12, 5A21, and 5A22. Good, so let's increase the complexity and start talking about, instead of scalar multiplication, start talking about matrix multiplication. So in this case, what happens when I have matrix A times matrix B? We'll get into it in a second, but what this is going to do is this is going to give us a matrix C, where each element of C is the sum of each element of C at Cij is equal to the sum from k equals 1 to n of aik times bkj. I'm going to get into that in a second. But this definition means that if I have these two elements, maybe matrix A has size m times n, matrix B has size n times l, matrix C, so the result is going to be the outer dimension, so m times l. This means that my inner dimensions must agree in order to have my indexing work out. Let's put this into an example, because I think it's going to be easier to see. So let's take a matrix A, and I'm going to fill it in with some numbers. So here we go. We're going to say 3, 1, 8, 6, 0, 4, and I'm going to multiply it by a 2 by 2 element shown here. So this matrix, so let's call this A and this B. So A is a 3 by 2 matrix, and B is a 2 by 2 matrix. So if I look, I can see that the inner dimensions agree, and we can see that my expected matrix has 3 rows and 2 columns based on the outer dimensions of A and B. So let's go through and set up what C might look like. I'm going to switch colors just so we can sort of see what's going on. So I'm going to now take this equation. So I'm going to be working on element 1, comma 1. So I'm going to go to, I'm going to take this first row of matrix A, and I'm going to take the first column of matrix B. So that first position is going to be the first 2 and the second 2. So 3 times 5 plus 1 times 7. All right? And this is going to be equal to 22. Right? So I'm taking the first element of each of those columns, the first element in row 1 of column A, the first element in column 1 of row B, and then multiplying those together, and then adding that result, so that's 3 times 5, adding that result to the second element in row 1 times of A times the second element in row B. All right, so let me switch color again. We're going to clear out our matrix to work on row 1, comma 2, element 1, comma 2. So I'm still in row 1. So maybe call this row 1. So I'm still in row 1, so I'm still taking that first row in A. But now, because I'm in column 2 of my answer, I'm going to take the second column of matrix B. So I'm once again going to do my multiplication. My first element in A is 3 times the first element in B is 9, plus that second element in A is 1, plus my second element in B, which is 2. So I can multiply this together. 3 times 9 is 27, plus 2 is 29, and that becomes my secondary element. All right, so now I'm ready to move on to row 2. So let me switch color again so that we have maybe a record that I haven't used yet, blue. So now I'm on to row 2. In this case, I want to take the second row from A, and for the first column of B, I want to take the first column in C, I want to take that second column in that first column in B. So we're going to just do this multiplication out. First element times the second element, so 8 times 5 plus 6 times 7. This is 82. And then for that next column over for that second column, I'm now going to take the second column in B. So we have 8 times 9 plus 6 times 2. And that is 84. Right? And then I can do this for the last row. Maybe we'll take orange. So that last row, I'm going to take 0 and 4 times 5 and 7. So 0 times 5 plus 4 times 7. This is 28. And then that last element, I keep that last row in A and I switch over to the secondary column of B. So 0 times 9 plus 4 times 2, which is 8. Put a 3. So overall, I'm left with a matrix that looks like this. We have 22 in 1, 1, 29 in 1, 2, 82 in 2, 1, 84 in 2, 2, 28 in 3, 1, and 8 in 3, 2. Okay, so in this case, A times B is equal to C. I want to make a quick note about mathematical operations. If you remember from scalar algebra, if I take A times B, this is equivalent to saying B times A, right? So 3 times 2 is equal to 2 times 3 is equal to 6. This is not true in linear algebra, in matrix math. Why is this not true? Well, remember, if I have this matrix 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, right? The inner dimension has to agree, right? So I have 3, 2, and I have a 2, 2 matrix, right? So let's say if I call this A and this B, and I flip them, so I have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. I'm not going to end up getting the same thing, right? So I could take this pair and this pair, and then this pair in order to get, say, my answer. And that wouldn't work, right? Because I have 1 times 1 plus 2 times 3, 1 times 1 plus 2 times 3. But what do I do with that number 5? I don't have anything there, so I'm stuck, right? So this doesn't work. So just remember that A times B does not equal B times A. So this is a key place that people mix up. So you got to keep this straight. I can't do these switching around of things. I have to go from left to right. Now that we have a better idea of how we can do matrix multiplication, we may start asking ourselves what other types of forms of matrices there are out there. And there's two that are I specifically want to talk about before we get a little bit into how we can put this matrix math into use. And so the first is called the matrix inverse. So a matrix inverse is a matrix that when I multiply a matrix A, that when I multiply it by A inverse, I end up getting the identity matrix. So to put an analogy, right, if I have a variable A equals 5, right, and I multiply 1 over 5 times 5, we get 1. Similarly, if I take a matrix A and I multiply it by its inverse matrix, negative A, I get that identity matrix, which is 1s all down the sides, on the diagonals, and 0s everywhere else. This is going to help us solve problems, matrix problems, in a second. Right? So the inverse matrix is demonstrated by that superscript -1, and when I take an inverse matrix times the matrix, I get that identity matrix. So the other type of operation that we want to talk about is the transpose of a matrix. So this is where I take maybe, say, a 3-row matrix. When I transpose it, I essentially switch all the rows in the columns to be, so it ends up going sideways. So right, so if I have 3 rows, 1 column, I take the transpose, that's then 1 row, 3 columns. This is going to just flip these different pieces, written out sort of in this notation way. A sub ij, I put that t to represent transpose, goes to a sub j comma I. So it just flips those pieces. All right, let's go back to linear algebra in terms of chemical engineering now that we've reminded ourselves a little bit about matrices and matrix math. Particularly what we're going to come out of this is matrices are going to provide a concise notation for representing and solving simultaneous linear equations. So let's take, for example, this case where I have 3 equations, 1, 2, 3, and 3 unknowns, 1, 2, 3. And I'm going to turn them into a matrix. What you can see, as I've already laid this out, is we have these coefficients in front of these equations, A1, A12, A12, sorry, A11, A12, A13. And I can take this and I can pull out these X1, X2, and X3s in order to form a matrix. All right? So if you remember, when I do matrix multiplication, I take each row times each column. So if I do this down here, we would get A11 x1 plus A12 times x2 plus A13 times x3 equals B1. Well, that's that first equation, right? So I've been able to eliminate all of those, all of the pluses, all those equal signs, and just sort of concatenate it. I can go one step farther and represent that first matrix by, say, the letter capital A. I can represent the x vector by, say, a vector x, and that equals by a letter B. And I can represent this whole big system of linear equations as matrix A times vector x equals vector B. Let's see how we can solve this now that we've built this up. So MATLAB is going to provide two ways of solving these systems of linear equations. But let's first talk through some ideas about how we can solve this. So let's say I know what AB, or matrix A is, I know what B is, and I want to know what is the vector X. In traditional algebra, I would say, in traditional algebra, I would take AX equals B, and I would divide B by A. But there is no such thing as division in matrix math. So I have to think of a different way to approach this. So the other way that I can do the equivalent thing is take inverse A times X equals inverse A times B, right? If this was traditional math, these two pieces are going to come together to form 1x equals inverse A times B. So in this way of solving this math problem, I only rely on multiplication because I have some number multiplied by another number, which equals 1. That leaves me with x equals that inverse number times b. So we can do the same thing now with matrices. I can take inverse A1 times matrix A. So the inverse matrix A times X equals A negative 1B. Remember that when I take these two matrices and I multiply them together, an inverse times itself, this should give me the inverse, the identity matrix. I now have the identity matrix times X equals A inverse times B. And then we can remember that the identity matrix times anything is just that plain matrix. So all of a sudden, I now have X equals inverse matrix A times B. This will now tell us how we can get A. Over the next few classes, we're going to talk about how we can do this. But until we get to that point, MATLAB can do this for us. So there's two ways that MATLAB is going to do this. So the first is using this inverse matrix method, where we can use the inverse function call, so inv parentheses a matrix, and that will first solve for the inverse matrix A1, and then it will complete the matrix multiplication necessary to solve that top equation. Or we can do what's called left division. Notice here that I'm not dividing B by A. I have, right? So if I sort of look up here, right, we would say X equals B over A. So that's called right-handed division. Here we have left-handed division where it's A, because remember I still have to multiply A, and then I use that backslash B to do the math. What's happening behind the scenes are a whole bunch of numerical methods that we're going to talk about over the next course. But what I want to notice, or what I want to say, is that even though we're not necessarily going to cover it, we're not going to cover it quite yet, that matrix inversion is much less efficient than this left division because there's extra processes involved that we'll get to over the next few classes. Okay, so to solve these matrices out, I can do X equals A left division B. We've now covered all the basics of matrix math. So I want to go through an example of how we might use this to solve a problem. I'm going to step away from chemical engineering for a quick second and talk about physics, as I think that this might give us a little bit easier time making sense of this. So let's assume that we have 3 bungee jumpers shown here that are all tied together by a bungee cord that's 20 meters long before it's stretched. So there's 20 meters there, 20 meters there, 20 meters there. They're all chained together. We want to know what the height, we want to know how far each bungee jumper is downwards if they're all tied together in the stretched mode. So what's X1, X2, and X3 off of its original tower, given some sort of spring constant K1, K2, K3, and then various masses of the people on the different masses of the bungee jumpers. Here I've listed out the bungee jumper, top, middle, and bottom, how much, what their mass is, what the spring constant is, so those K1, K2, K3, and what the unstretched cord is. If I go over to the right and draw free body diagrams for each bungee jumper, we can see that there's 3 forces acting on the first bungee jumper. So the first force is K1, X1, due to the spring holding the bungee jumper up. There's his mass pulling him down, and then the force coming from the second spring that's tied to the second bungee jumper. That second bungee jumper also has 3 forces acting on her. One case, the force pulling up, so K2 times X2 minus X1, right, to take into account how far he's been stretched out. Her mass, and then the force pulling down on her from the third bungee jumper, and then the third bungee jumper has only 2 forces acting on her, an upward force from the cord, and then the downward force of gravity. So I can take these free body diagrams using physics, using Newton's equation, determine 3 simultaneous equations. So Newton's equations say m1 times the change in position, the second derivative position with respect to time squared equals the sum of the forces. So m1g, k2 x2 minus x1, and k1 x1. And I can write the same thing for bungee jumper 2 and 3. If I'm only interested in their behavior when they're not moving, all of these second derivatives go to 0. So I can rewrite the equations as below. So I can rearrange so that I have x1, all the x1s in the first place, all the x2s sort of terms in that second column, and all the x3s in the third column. Now that we have our 3 equations written out, we can convert this into an appropriate form for matrix math. The first step, of course, is recognizing that there's this extra term in the first equation that is a 0 times x3. This way we have 3 variables, x1, x2, x3 in that first equation. And then we can do the same thing down here with the third equation where we have in a 0 times x1 to round out and make sure that we have that x1 term in the third equation. So I can rewrite these equations and put them in this form, right? So we can see that we're already looking sort of like this matrix math form, right? So I can look and see this first k1 plus k2 term would correspond to that a1, negative k2 would correspond to a12, and then 0 would correspond to a13. And then b would be our m1g. We can do the same thing for each of these different equations and put these into a matrix. So let's do that. I can rewrite each of these equations, or we can correlate each of these equations to a spot in our matrix form, and it just becomes an issue of determining what these k1 plus k2 are that we know are going to end up in a11. So going back to that original problem, we listed, we had what our masses were and what our different spring constants were. So we can look, for example, what a11 should be, which is k1 plus k2, which is 50 plus 100 from our table, which should be 150. And we could then calculate what a12 is, which is negative k2. This would be negative 100. And then a13 is 0. Right? And we can do the same thing for the second line equation and the third line equation. And if we do this, I guess I'll erase that second example. We can fill in that matrix. Here was that 150 coming from a12, the negative 100, which corresponded to negative k2, 0, which corresponded to that 0. And then same thing, we have negative 100 for that, negative k2 for that second row first column, k2 plus k3, which would be 150 by taking these two together for that second row second column, negative k3 for the third column from up here, that's negative 50. We see the negative 50 there. And then for that last row, 0, negative 50, 50. We can then do the same thing for our for those b's, right? We can take m times g, so 9.81 times 60, and that's 588.6. Same thing for B2, which is 70 times 9.86, sorry, 9.81, and then B3 is 80 times 9.81. So now we've set up this equation in matrix form. And the question becomes, how can we solve this? In MATLAB, we need to go in and we need to put in our matrices. So here I've typed in this top matrix, so that A matrix or that K matrix into MATLAB, 150, negative 100, 0, semicolon to tell MATLAB we're going into the next line, negative 100, 150, negative 50 for the second line, and 0, negative 50, 50 for the third line. Okay. And if I hit enter, we should see that K matrix pop out that matches exactly what we had in our equation. And then we can do the same thing for our mg vertical vector, just popping in the numbers 588.6, semicolon 686.7, semicolon 784.8. We want to make sure that we're using that semicolon so that we end up with a vertical array. Conversely, we could have made a horizontal array and then transposed it in order to get that vertical configuration that we need. So once we have those variables stored, we're ready to solve the equation using left division. Remember, this is the faster method, so we can type in our x, so our position is k left divided by mg. Remember, we can't do matrix divided by matrix. We have to do that left division to actually get the version we want. Right? And if we do that, we end up finding the position of the first bungee jumper is 41 meters, 55 meters for the second, and 71 for the third. We can solve this in the other method using our inverse matrix, where here we say x is equal to the inverse parentheses k times mg. And we'll see that we get the exact same result as we do using back division. But once again, using that inverse matrix multiplication is going to be significantly slower than left division. One last set to solve the problem is that we have to remember that the chords were 20 meters before they were stretched, right? So this x is the distance of the chord unstretched, so say this is the chord, this is the stretched distance, and that 41 is that stretched distance. So we need to add back in the 20 meters for the chord to get the true distance. So the first one we need to add in 20 meters. The second one we need to add in 40 meters because there's two lengths of chord, and then the third bungee jumper we need to add in 60 meters to account for there being 3 unstretched chords. This then rounds out the end of that problem, and hopefully you've seen how we can take a mathematical problem, turn it into a series of linear equations, and then use matrix math to solve that relatively straightforwardly. So by the end of this lecture, hopefully you are feeling quite familiar now with matrix notation. You're able to identify special types of matrices, specifically square matrices, the identity matrix, diagonal matrix, symmetric upper and lower triangular and banded or particularly tridiagonal systems. You feel comfortable or start feeling comfortable with matrix multiplication. You feel comfortable taking a series or a system of linear equations and converting them into matrix form, and then understand how we can use either left division or multiplication by a matrix inverse in MATLAB to solve the equation. Okay, see you in class.